So thanks a lot for inviting me here. I'm really honored. And also, Sushi mentioned a lot about my productive team. That's why I list 4 students who work with me. Taha, Zhengping, David, and Wenjie. They are the major driving forces for the work that I'm going to present in here. And also, this is joint collaboration with Ying Fan, who is a statistician. He is a superstar in statistics domain. And then you are going to see some merging trend in terms of machine learning and statistics as well. So thank you. I'm going to talk a little bit about our recent research work on learning and mining from large-scale time series data. So we now know that time series data pretty much emerge everywhere in many applications, such as climate, biology, healthcare, and etc. So next, I'm just going to give 2 examples. One is healthcare application, especially in the application that we work on. We go to this intensive critical unit, that is the ICU, known as ICU, where they got all the sensors put on the patients, and they will collect all the sensor time series data. And for us, as a computer scientist, especially machine learning researchers, we want to analyze this data. We can do a lot of interesting analysis tasks, such as characterizing the disease, making predictions, or even doing some patients clustering or patients like me finding. So there are a lot of research interest in there so that we can apply machine learning algorithms. Another application is climate, where right now, due to the technology of sensor and satellite, we'll be able to also get access to large amount of climate-related time series data. And in this particular domain, simulation model has been the major driving forces that is built based on physical-based models. And just recently, because of the flood of data, so that machine learning algorithms started to play a major role. And we have this interesting and emerging field called climate informatics, where we want to apply machine learning algorithms to analyze climate data as well. In there, we're going to face multi-resolution spatio-temporal data, and also a lot of challenging statistical problems. For example, we're interested in extreme events such as drought and heat. And these are essentially not very easily captured by these Gaussian assumptions that we have known. Therefore, that this essentially raises a lot of interesting challenges and also give us opportunities so that we can develop machine learning algorithm and solve interesting problems in the climate domain. So when I prepared the talk, that I was thinking, okay, probably I'm going to talk about 2 applications. And then when I sit back and realize, oh, Johns Hopkins is basically has the best hospital in the nation, that there's no way that I can escape without telling the applications in healthcare. So for the rest of the talk, I'm going to use mainly the healthcare application as motivating examples and showing experiment results. But at the same time, that I probably will mention a few things on the climate applications. So when we look at all these interesting problems, basically that we will be provided a series of research opportunities so that we can do the analysis for time series learning and mining. Here I just gave some examples. For example, we can do temporal dependence discovery. That is, we want to recover which current values of some subset of time series will be useful in predicting the future values for a time series that we're interested. Or we can go with modeling, that is mostly prediction task, or we can go with feature learning, that is extracting informative features from the time series observation, retrieval, magic learning, clustering, and anomaly detection. Basically, that there are so many interesting tasks that we can work on for time series mining and learning. And when we look at the literature, there's basically that a rich amount of excellent work in statistics, economics, finance, data mining, and machine learning. So my major research interest is just trying to leverage the advances in all of these areas, trying to analyze the time series data, and then so that we can develop more efficient and also effective machine learning solutions. So that is essentially the central theme for the rest of the talk. And when we look at the challenges, and everyone knows about the challenges in all these big data analysis, basically that we will be confronted with high-dimensional data, because when you look at a time series itself is high dimension. On the same time, we may gather millions of time series data that also provides another dimensionality for high dimensions. On the other side, we also have large scale because of the sensor technology and because of the breakthroughs in other technology to give us access to the scalability, to the large scale data set, so that scalability is an issue. And obviously, complexity is another issue, because when we look at time series data, it's not only involving all this complexity that is associated with ID data, but also with the temporal dependence and also with the spatial dependence. This all brings out the complexity word that we have never encountered in the world of ID data analysis. So in order to solve all these problems and the challenges, and therefore we have to resort into recent advances in machine learning to solve all these practical challenges in terms of high dimensionality, large scale, and also complexity. So for the rest of the talk, I'm going to give you 2 examples. In my previous tour that I usually give 3 examples to talk about temporal dependence discovery, spatial temporal prediction modeling, and also feature learning. And this year, I just want to give more detailed, more specific examples, and also more our recent work. So the first example I'm going to give you is actually on time series clustering, where we developed the functional subspace clustering algorithm. Essentially, it is a nice merging theme in statistics, that is functional data analysis, together with the machine learning theme in subspace clustering, which is a marriage between these 2 areas. And there you can see that we actually use functional analysis to solve the complexity problem in time series data. And then in order to solve the high dimensionality challenges, we want the model to be relatively sparse. And then to solve the scalability, we're going to develop the greedy algorithm so that we'll be able to get very efficient algorithms to be applicable to large scale data. And another example I'm going to give is on time series feature learning. I know that right now in machine learning field, there's no way that you can go around without talking about deep learning. Obviously, that we also want to be part of the theme, but at the same time, we want to talk about the unique contributions. That is how we can apply deep neural network to a particular application where the data may be limited, where we can actually resort to prior knowledge or domain knowledge to help the training. At the same time, when the data comes in stream, especially in time series data, we're going to see the data comes at individual timestamp, where incremental update will be much more desirable than batch update to solve the scalability issues. So that's kind of the big pictures of where we're going. So next, I'm going to first talk about the time series clustering problem, and then later followed by the feature learning problem. So first, I would like to introduce, give a little bit introduction on the functional data analysis. So when we say functional data, basically this means that we're going to have multivariate data with an ordering on the dimensions. This is a very generic definition, but basically they represent a large variety of complex structured data types in the real world, something that we are very familiar with, and that is in the context of this particular talk, time series is actually a functional data. And when you look at the more general pictures, that images or shapes, these are all basically, you can think of them as functional data with specific ordering of the observations or the data points, and also we are interested more about the dependence and also the correlations between the data points. So the problem and definition for our specific example is that we're interested in clustering these functional data. Here I gave the example in the healthcare domain. Let's say that we're going to collect the vital signs of patients. For example, the heart rate, the body temperature, the oxygen rate, and etc. And then we want to cluster these patients in different groups so that we can probably predict the morality of a patient, whether a patient actually will survive or they will die. right? So you can think of them as a very general and also very specific example, not limited to healthcare, but also in many applications. We may be interested in doing time series clustering problem. And then when we look at the specific challenges, then we realize that time series clustering, the problem itself is quite challenging and unique compared with ID ones. The first one is about high dimensionality and the latent structures. We know that functional data, because they're multivariate, usually they are always high dimensionals. And in high dimensionals data analysis, that the common issue is that the distance metric is not usually well defined. I mean, how do we define the similarity between the time series is still an open problem, and similarly true for many other functional data as well. So the other problem is that usually these data will exhibit complex latent structures. This means that the observations may actually were generated from another latent space that is relatively complex, and we want to learn from it. The example we can give again in healthcare application, where we get cell disease will exhibit similar symptoms. And this is essentially means that even though that we saw the labels or the clustering results are very different, but when we look at the particular symptoms or the fundamental mechanism governing the human body, they may actually map into very similar latent space which we want to learn about. To address this type of challenges, actually, there's already this really interesting theme in machine learning that already gave a preview that essentially will be the subspace clustering. So many of you have already known the concept. I'm just giving you a very quick introduction. So the main idea tries to say that we assume all the data point, each data point in an S-dimensional linear subspace can actually be represented as a linear combination of S or less other data points in the same subspace. And therefore, in order to seek for the S-dimension representation, what we can do is that we can actually perform this n-sparse regression problem. That is, for each example yi, I'm going to do a regression over all the other examples. That is, here j will iterate over all the examples except for the ith example. And then since that we assume that this will be example can be represented by s or less number of other examples, we can say that we want the number of non-zero elements in my regression coefficients, that is bi as a vector, the L0 norm, that is the non-zero elements will be, the number of non-zero elements will be smaller or equal to s. Okay, so once we solve this sparse regression problem, then we're going to get the regression coefficients. And for subspace clustering, what they will do is that after that, we're going to apply the spectral clustering to this particular matrix, that is B norm plus B norm transpose, which will literally represent a compact representation in terms of the similarity between different between different examples. And then applying spectrum clustering, that means that we're going to get a relatively nice clustering results. There's a lot of literature discussing the nice theoretical properties so that they will be able to very nicely capture the distances. They will very nicely recover the latent space associated with the data generation process. So I'm not going to iterate them. But basically, that you can just fully trust me that it is very much backed up, and then that is why that there's a lot of research work on this particular area. It is also very simple because basically that we can just simply applying sparse regression problem and then get this regression coefficients, and later we'll be able to get the clustering results. So this is addressing the first challenge, that is high dimensionality and also the latent structures. So the other challenge is that in time series data or in other functional data, we will force the deformations of the functions. That is, even though the functional data, they actually belong to the same cluster, they may actually belong to the same cluster after some deformations. So one example is, let's say that we have time series observations of different patients, let's say heart rate, and then we literally need to do some warping of the time series so that we can align the peaks and also the valleys, so that when we align them together, we'll see, oh, these two patients are very similar. This means that we need to do some transformation, we need to do some deformation or shifts so that we will be able to reveal the true similarity between the time series or the images. So in order to address this particular problem, our goal is trying to say that we want to utilize the nice framework of the subspace clustering, but at the same time that we want to utilize recent advances in statistics on functional data analysis so that we will be able to integrate or solve the problem of deformation for time series and at the same time doing the clustering. So that's essentially our goal for this first problem. And then we want to mention a little bit of the existing approach. Many people have developed different type of time series clustering algorithm, including Sushi in here, that developing machine learning algorithms for healthcare applications. But here, basically, we summarize them into 3 different themes. The first one is that they want to fit a generative sequential models, and then they will perform just regular structure clustering algorithms. So here are some examples, like Kim and Smith. Already in 2006, they talk about using functional generative models so that it will construct the nice similarity between time series and then to solve the problem. The issue with this particular approaches is that the data may not actually follow the assumed generative process. There's always have to be some assumptions associated with them. The other one is that we want to project them into a special basis function. And the issue with this particular solution is that we need expert knowledge so that we have to choose the right basis function. And most of the time, we actually will not be able to know what will be the right basis function. And that becomes the chicken and egg problem, right? We want a very nice clustering results. But in order to get there, we need the basis function. But once where we get the basis function, sometimes they also rely a lot on the clustering results. And therefore, that the domain knowledge essentially will be a must to choose the basis function. But usually, this may not necessarily be available in some of the domains. And the third one is essentially will be implicitly enumerating all the possible deformations. And this recent work by Yuan Li, basically these are statisticians. They have developed some nice algorithm based on functional data analysis. In there, they literally need to enumerate all the different type of deformations in order to do their calculation. However, the issue obviously you can see is that the number of deformation can be very large. And here we give an example that is the number. Let's say we have two time series T1, T2. Essentially, we need to about exponential term of T1 plus T2 number of different type of deformation functions to enumerate all of them in order to get the solution. So that also obviously give us the challenges in terms of solving the scalability part. If we were given a time series observations of 1,000 or 10,000 timestamps, then we literally run into serious problems. All right, so given all these existing approaches and what they have done on all these issues, that's now we would like to introduce our technique, that is the functional subspace clustering algorithm. Our particular solution is that we want to define a deformed manifold. This is trying to say that is we first will define the subspace model. This is essentially will be our assumptions. This is assume how the data will be generated. We want to say that even though that we do have this assumption, it is relatively general. As you will see that many of the functional operators that we define actually belong to these classes. forces. So first, let me explain what is assumption, and then later I will tell you why we want this particular assumption. So the subspace model assumption is as follows. Let's say that I have some functions xi. It can be a curve or it can be a time series. We'll say that they are selected from L number of manifolds, and we represent each of them as SL. So L will iterate from 1 to L, big L, and then let's assume that we'll be given some basis function. Obviously, we do not know, and then I will tell you right now that in fact we do not model them at all in our particular algorithm. But let's just assume there's some basis functions phi L associated with each subspace, and then each manifold SL can actually be defined as follows. That is, X can actually be a D, essentially will be the operator that is a functional operator, and inside this will be simply a linear combination. Alpha K here will be just the combination coefficients, and then phi K will be the basis function that we defined. So this means that for each particular example, this can actually be represented as a linear combination of the basis function after some deformation functions. Okay, and then we'll say that the observations will be noisy. This means that my observations yi will literally be xi plus some noisy term. And this will be assumption. That is how the data will be generated. As you can see, this is a kind of assumption that gave us some relatively simpler form in terms of the linear combination of the basis function together with an operator. And then the benefit of doing this assumption is that essentially we are going to have the self-expressive property. That means that if the deformation is actually a linear maps, that is the deformation function operator D that we have in here is linear maps, then we can actually have this self-expressiveness. That means for each particular example xi in my observation, it can literally be represented as a linear combination. That is, beta defines the coefficients, and also djxi xj. This means that we're going to do some deformation operation. dj here is just the deformation function. Xj will be meaning that each other examples. So that means is that if we actually have this assumption, the subspace model assumption that I described just now, this literally will give us a very nice self-expressive property. For each individual examples that I see here will actually be a linear combination after the deformation of the observations that we see in the whole data set. So this gives us a very nice power, because once we see this self-expressive power, then we will be able to combine this together with the subspace clustering. So first, I also want to say that even though we have defined these assumptions that I mentioned, they actually literally define a very rich family of classes of deformation will satisfy this particular condition. For example, when we talk about the reweighting, right, we want to reweighting different type of the scales, or we want to do some type of permutation, or especially for the deformation in terms of time warping, they will all belong to this classes, so that we can apply some of the general techniques that we applied before, for example, dynamic time warping or rescaling, or other type of classical operators on top of it. So that's the nice thing about the flexibility of this type of operators. All right, so once we have this self-expressive power, as I mentioned, we're going to do the same thing as the subspace clustering. If you remember, what they did before is that we're going to do a sparse regression over each examples and then get a regression coefficient. We're going to do exactly the same thing as before, except now we're actually going to have an operator dj that will be providing a deformation of of each individual observations that we see. And now the optimization problem will be involving two variables. One is Bij, that essentially will be the regression coefficients. That is very classical. People have done that all the time. At the same time, we also have Dj, that will be deformation functions that we have to search for. And therefore, this becomes an optimization problem involving both Bij and Dj. And we have the similar constraint as before. That is Bij, we want the number of non-zero elements to be smaller or equal to S. That is why we have the constraint in there. All right, so after that, the rest of the thing will be very generic. That is, we first need to essentially think about what type of optimization algorithm that we can apply to this framework. Okay, that's the first thing. The second thing is that here we have Dj. I'm talking very abstract level. Probably I saw a few people looking at me with puzzling faces. That where does the D come from? What exactly is D? So that is another problem. That is for time series data. What type of deformation function operators that we can define in there? So we're going to solve these two problems in the rest of the talk. I already talked about the optimization over the operators and also the deformation. So next we're going to first talk about the optimization problem. I'm not going to iterate the specific details, but the basic idea is very simple. In statistics, people, and also in machine learning these days, that when we talk about selecting the variables, there's this trend that is called using the greedy-based algorithm. And we are following the similar thing, the similar framework. That is, for each particular iteration, we're going to do the three steps. The first one is that we're going to find the best deformation across all the functions. Here, the best deformation, D star, is literally defined as maximizing a criterion that we define here. And this is basically, we define the angle of yi, that is our response variable, that is the time series that we're interested, and also the deformation of yj, that is after the deformed operator of the time series, we want to define the angle between these two. And we want the D star that can maximize the angle between yi and also the deformed time series. And then the second step is that we're going to add this D star into our deformed set that initially we set as announced as an empty set, and then gradually we'll add them in. And then we also do this optional orthogonal projection step. That means that we're going to map the features, map the observations, so that we can go back to the original space. This is literally trying to improve the accuracy. And then essentially, if we do this all the time, or iteratively, we'll be able to get the set of the operators at the same time. Then we can also get the regression coefficients. That part is more generic. That's why we didn't describe it in here. The problem, as I motivated earlier, is that we need to find an oracle that can give us the best deformation, because here this is still a very big searching space. And that essentially comes to the second question, that is how we can actually identify all the deformation operators. So here we just want to mention that obviously that we can give performance guarantees. This is relatively generic. When I talk with people, they ask me what type of theory we do. I mean, I would say that we literally just apply what existing in statistical domain and then define it specifically for our algorithms, the machine learning algorithm that we developed. The theorem just basically means that we will be able to control the selection of the neighbors by the following. That is, for any particular function in the L space, our algorithm will only select the functions from the same subspace if the termination criterion is said to be larger than the specific value. And when we look at a specific value, here theta L essentially will be the minimum principal angle that we defined, which I defined in here. This is essentially the angle that we define in here. And the second part is RL. Here, this RL will be this radiance that will be covering the data from the L space. So intuitively, you can think of them as measuring the data sparsity in each subspace. I'm not going to iterate in the details. We have the very detailed proof in the supplementary materials of this ICML paper. You're definitely welcome to check it out. But basically, we just want to say that we do have some nice theoretical guarantees in terms of the algorithm that we developed. The next thing is that the operators, that is how we are going to look for the warping deformations. So the way that we do it is as follows. For time series data, we can think of the time warping as can be represented as an indicator vector. So let's say that we have all these different type of indicators here. I give some example. We have Z1, Z2, Z3, and Z4, and each of them will represent a unit vector with only one element equal to 0. And we have Z1 until Z4. This means that we are going to define which particular time series, what particular timestamp will be corresponding to the deformed time series stamp. So here, for example, I have my Y observations. Right here is my Y, and then given these operators Z1, Z2, and Z4 until Z4, we say, okay, we're going to select the first one as the first timestamp in my deformed time series, second one to the second one, and third, we're going to ignore them, and the third one, fourth one will be the third one, etc. So after defining these operators, we can essentially can say that the deformed time series dy can literally be represented as a transformation that Z1 transpose Y until ZT transpose Y. And essentially, these will be the indicator functions, the indicator vectors that we are looking for. And we talk about this maximize the principal angles. That is, R will be our selected space here. Essentially, they represent yi that we have in mind, and then dy essentially will be the new deformed time series by doing these operators, and then we want to maximize this principal angle. So the optimization problem literally can be reduced into a very relatively straightforward optimization problem. That is, we're looking for these indicators zk that can maximize the angle, but if we do the inverse, that will be literally minimize the inverse of the principal angle that we defined. And we only have the requirement, that is ZKL, they will be either 0 or 1, and then we also want the summation of ZKL over L will be equal to 1. So after the rest of the thing is that we're going to relax this assumption that ZKL will be only 0 and 1. We want to relax them into the value between 0 and 1. And this becomes a very standard optimization problem. The rest of the thing is straightforward. As I mentioned, then we're going to solve the problem using the Frank-Wolfe algorithms to do with the linear search. So this is how we're going to select the deformation operators. As you can see, that is, we do a one-step relaxation so that we can do the optimization much easily. Otherwise, this will be a combinatorial optimization problem, which may be difficult, especially for the real applications that we're working on. All right. So with that, that hopefully gave you a big picture of how the subspace clustering algorithm works. Basically, that we have the subspace assumptions so that we'll have the self-expressive property, and then we'll apply the subspace clustering algorithm as before. But the optimization problem becomes difficult. That's why we developed the greedy algorithm. At the same time, doing this operator search using the relaxed optimization algorithm. That hopefully summarizes what we did in this paper. Question, yes?
So it seems like you never wanted the indicator variables anyway. It seems like by relaxing that, you're searching over a larger space of distortions.
Yes.
So it seems like you gain something by doing the relaxation.
Yes, that's another. I totally agree with you. So when we look at it, when we look at where the gain comes from, right now that I'll show you some results. We try to see what will be the learned subspace and also what will be the gain come from. We have a little bit difficult time to explain the features of the latent space, the subspace that we learn because of that issue. Yes. So that's kind of a trick. I think that's kind of a pros and cons. There is pros and cons in between. Yes, Rishi.
Actually learning the information here, right? The information, it's a class of functions that you're allowed to use, and we're trying to figure out what's the information that gives you the minimum distance
Yes.
between one given time sequence at this time.
Yes.
That gives us.
Yeah.
So then the question is, so that's one. And then the second question is, the basis function that you said you wanted.
No, we're not going to learn it because of the self-expressiveness, we do not need to learn the basis function anymore. We can just say the time series can be represented as a linear combination of the deformation of the time series. That's the beauty of it.
Essentially, what you're uncovering is the nearest neighborhood for every
Yes.
individual
Yes.
time. And the benefit of doing this is that once you have this neighborhood structure, then the typical algorithms that you would do in subspace clustering, you could rethink. Essentially, it gives you a non-parametric representation.
Exactly, yes. So you can think of them as like a non-parametric way to do feature learning, but we don't want to go there because then the people will always ask the question, okay, because I am going to talk about deep learning in the next chapter, then which one is better, right? And I think it's really different methodology and also its uses is very different. I truly believe that for finding the neighborhood and also for clustering problem, the subspace clustering seems to make a lot of sense because they are trying to identify the latent subspace even though we don't explicitly uncover them, and also to identify the neighbors. I think that's kind of the beauty of the algorithm. Obviously, it's also simple.
So a couple more questions.
Uh-huh.
So I guess I think there are actually algorithms that learn the basis function and learn information. So in a way, can you comment a little bit on when might you want to consider using this as opposed to something else? Because I don't think the strength is just that here, that we don't have ways of learning information. So we don't have, like, that we have to say a generative model that is extremely, that biases people to discover a structure that controls. So I think there ought to be other benefits. So can you give an intuition or sort of describe a little bit of what are cases where this would be particularly useful?
I'm not sure where you are hinting at. I think that you already have an answer in your mind, but I'm just giving it a try, right? For cases like this, let's say that, for the time series, when we look at this particular problem is that we literally have both the problem of finding the neighbors and also defining the metric that we want to use, right? This is also becomes a chicken and egg problem. Let's say you go with these generative approaches or with all these approaches that I reviewed at the beginning of the talk. Most likely you have to do this as a two-step process. That is, you get some way to define your metric and then you do some clustering. But this one is literally trying to say that is, given this is a chicken and egg problem, why don't we just do this within one framework? Why don't we do the search together? I think that's one of the benefits that we may be able to get. And so that's, I don't know, do you have any further suggestions or comments on that?
So I could essentially, in a way, I am dependent on that sort of information.
Yes.
Which allows me to define which series I use for each other, and my neighborhood structure depends on that. So
No, but you didn't define, but you only define the operators in the sense that you said there's going to be this deformation or there's going to be changing the weight, but you do not define, okay, how much weight we're going to change and how I'm going to deform it, right? I think from that perspective, that just give you a classes of operators that you can choose from. Essentially, that will be given more parameters that we can work on, rather than that right now that we just work on very fixed set of operators. This means that we're given a family of operators, and you can choose from. So that gives us a little bit more freedom. Okay. Question? Yes.
Are you learning a separate transformation each time?
Yes.
Or is it,
Yes, it's separated for each pair of ing. That's also why it is computationally. I will hint at the end of the talk that we can still. This is still affordable on all the healthcare data that we played. But if let's say we go with really bigger data set, let's say on images with millions of them, then we do have this issue because for every pair we need to look for the best one. But that's also the beauty, right? Because we want to find this specific neighbors that is for each individual examples the best one. So there is a cost associated with it, but there's also benefit comes with it. Okay. All right. So with that, I just want to show some examples. First, we conduct experiments on synthetic data set. This is more controlled because right now we already defined the basis function. They will look like this. There will be two sets of basis function. One of them will look like this one, and the other will define as this. And then after that, we're going to have two types of deformations, including time shifts and time warping. And then based on the basis function and also the operators that we defined, then we can generate observations. And since we know the basis function, how they are actually generated, we will know the ground truth. That is what will be the classroom results. So here I'm just going to show you some experiment results. We have two plots. One is by varying the length of the time series. That is, we are going to generate longer time series observations. The second one is that we're going to vary the number of data points per cluster. And then we have a series of baselines. The first one, the blue one, that is representing our algorithm. That is the functional subspace clustering. And here TW literally means dynamic time warping as the oracle. And then we have the green one, that is subspace clustering. We also have other two-step processes. That is applying, let's say, DTW plus SC. This means that applying DTW, and then after that we apply subspace clustering. ED means Euclidean distance, apply subspace clustering. GAK plus SC means that the global alignment kernel, that is another similarity metric that people have developed for time series data, and then after that apply subspace clustering. So basically that we enumerate all the strong baselines that we have think of in the literature, and then here is the result in terms of the clustering error rate. So our algorithm basically that we're able to guess the lowest error rate in both cases, and also some observations. That is, when we increase the number of time series, this means that we'll be able to better learn the basis function and the better representation, and that is why that we're going to have reduced error rate as we increase the number of time series. And similarly, when we increase the number of data points, the more data points we have, we'll be able also to learn a better representation. That's why that we're going to get better results when we increase the number of examples per cluster. This is not necessarily true for many other examples. So that is another benefit that we can get. That is, if the data are truly generated by some latent subspace, and by getting more observations, we will, in general, will be able to do better. And the next one is that I'm going to show you the results on the clinical data sets. This will include the ICU data set. This is essentially the data set that we collected through our the collaborator collected at Children's Hospital Los Angeles. We have 13 variables, including all these vital signs such as heart rate, body temperature, oxygen rate, and stuff like that. And then this will be 24 hours. The next data set is the PhysioNet. That is kind of a computation which extract a subset of the public mimic data set. It has 18 variables and 48 hours. This one, they do have a binary label, and in that test, they want to predict whether the patient survive or not. And they do have the ground truth that we will be using. And obviously that we want to predict the mortality of the patient, as I mentioned. So here I'm just going to show, first is that the data set are very challenging. Here what we plot is for the PhysioNet data set for different type of variables, glucose, HCO3 and stuff. And then we have plotted the mean value for different classes. The red one represents the deceased patients. The blue one represents the survived patient. Okay, and then the error bar means that this is the kind of the variances. As you can see that they pretty much overlap a lot. It's quite a challenging task. It's almost indistinguishable by naked eyes. And then we apply our algorithm. Obviously that we get the best results so that we can publish the paper. But basically, if we look at the predictive AUC score, our method, that is functional subspace clustering, FSC, basically that it will get better prediction results compared with all the other baselines. So that sort of complete the numerical evaluation. So while we were preparing for the paper, I keep on pressing my students and let's find some informative features to show. It will be much nicer that if we can show what type of features or what type of subspace that we have learned. And due to the reason that I just mentioned to you, because we relaxed the optimization problem, we were not able to find anything informative yet. That's kind of an ongoing work where we want to see how we will be able to interpret the results. That is how we can better characterize the cluster results than just showing the numbers. So just summarize that basically that the challenges in functional data analysis or time series clustering in general is that high dimensionality, complex latent structures, and there's a lot of possible deformation steps. Our solution, the functional subspace clustering, they basically unify the subspace clustering algorithm, and that is very popular in machine learning together with the functional data analysis, which is a major trend in statistics. And we want to provide like a unified framework and also provide efficient algorithm using a greedy search. I talk about the future where one is the scaling up. That's an issue because we need to find the best alignment or best deformation for each pair. That takes a lot of time. The other one is that we also want to find the nice theoretical guarantees and also the interpretations of the subspace that we learned. Okay. So with that, I want to just stop a little bit to see if you have further questions regarding to the topic, because next one I'm going to move really fast to talk about the deep learning. Yes?
It looks like with SSC subspace, normal subspace clustering, do you have an intuition for why on the ICU data the FSC seems sort of
Yes.
on par with it? Like,
Yes, because what we find out is that for the ICU data, they are all just limited 24 hours. And when they collected the data, the doctors literally just gave us the 24 hours that they think that are informative. So they are pretty much a little bit aligned already. By self-selection process. I think that's possibly could be one of the issues. We have a little bit a long time, just a difficulty trying to beat the baseline because somehow the data was collected in a way that simple algorithm works. So I think that's probably one of the reasons because the doctors have, I mean, when they process the data, they already have some way to do the shifting already. Yeah. All right. So next, I'm going to talk about the feature learning problem. I'm going to talk really fast because most of the techniques are relatively straightforward, but I do want to talk about why we are working on it. In this task that we're interested in doing phenotyping, also called as biomarkers, Sushi also again did a lot of work, and I think Ilya also trying to work on something along the line. But basically that we want to find attributes or characterization of the disease or the patients with the disease so that we will be able to separate the patients into meaningful groups. We can make better predictions. And this is something that the doctors very much are interested. And when we look at the specific data, we can say that we are going to be given these raw time series observations, and then we just want to look at some representative features. And I can tell you, probably a higher a lower oxygen rate or a higher heart rate will probably means that this will be a characterization of a heart failure. So intuitively, that we can think of them as more or less like the feature learning problem in machine learning. And I don't think I need to iterate you about how deep learning have conquered the world in terms of feature representation. Every person I talk with that you have worked on deep learning as well. So we can think it's more like a natural way to do it. But the question is that how we are going to do this for the healthcare time series data. I know that in many applications, let's say the language, natural language processing, many of the people in the audience are working on, they literally have a lot of data. And that means that you can have a lot of things to train the neural network to work. But in healthcare data, that's the first thing that we realized. That is, I went to the doctors and they said, I got really brilliant data set. I have 400 patients. And I was like, 400, that's too small. I don't know what I can do with it. So the data is relatively small. And also, the searching space is huge, right? Because when we look at the characterization, we do have observations from the time series of 24 hours, but obviously that they only appear, the characterization pattern, they only appear at very short window. And we do not know which window to search for. That's another challenge. That is, we know it appears somewhere within this longer window, but where exactly, how long a time period appears and what is the characterization, we literally don't know. So that's another challenge that we're facing. So solve the second problem that I actually was trained as in Language Technology Institute at CMU. So the one that we tend to use, and also in biology field, is using this window-based approaches that we're going to search over different windows, and hopefully we will be able to identify the one that is most predictive. So that part has sort of been taken care of. That is, we have the time series observation that says, say I take a window of 6 or a window of 10 or window of 12, and then I'm just varying the windows and doing the search. And you can think of them for each window size, we're going to train a neural network. That's kind of the idea. All right, so the label sparsity, that's kind of the challenge I mentioned. That is, how we can handle the sparsity in our labels, and also the limited number of examples that we can train or utilize to train the neural network. And the way that we resolve the problem is that we want to incorporate existing domain knowledge because in medical domain, they have defined a lot of good ontology to define the relationship between the disease. And we want to utilize that to train the neural network. And this is what essentially happens, that you can just think of them as a neural network. On the top level, that will be Y1, Y2, Y3. This will represent different type of disease labels. Obviously, this will be 0 or 1 for individual patients. Okay, and then we're going to train, this will be our input, that is x1 to x4. In this particular paper, in KDD, we used the autoencoder, but we are currently investigating also the recurrent neural network for time series, which is a natural option. But it really doesn't matter, essentially, the architecture. But basically what we can do is that we want to utilize the relationship between different disease, that is on the top level, Y1 to Y3. And then the way that we define it is essentially we're going to utilize this Laplacian regularizer to make sure that the disease with similar disease type, the corresponding weight, that is beta, the corresponding to different type of disease, will be similar. Okay, that is why that here we have the loss function L, and then we're going to train this neural network as before. I'm not going to iterate, but at the same time we have this Laplacian regularizer. Here L will be constructed from C minor by C minus A, and here A basically will be the label similarity. That is how different disease will be similar. And we use both the tree-based prior and also use the co-occurrence prior, that is based on the data. They will tell us how similar different disease will be. So that sort of help us to solve the first problem. And the second problem is about the scalability. I know that people in Google and Facebook, they handle this all the time. I'm not going to iterate. But what we are trying to do is that we literally are going to do incremental training. This means that, let's say I train a neural network with a window of 6. Now I want to extend it to train a neural network with a window size of 10. We can obviously do all the total retraining. This takes a long time. That's one thing. The other thing is that because we do not have that large amount of data to train the neural network with larger window size, then we run into the problem that is we're not going to learn anything meaningful. And that is why also we want to start with something that we trained already that have relatively larger examples, and then migrate them into the bigger neural network. That's kind of the idea. And the only challenge that we're facing is that when we look at the structures, we realize that is the neural network, they are not only changing in terms of the feature size that people have studied. Hong-Hai Lee from U Michigan, they have already published a paper talking about when we increase the number of input features, and then there is some increment training algorithm that have already, we can do it relatively well. The challenge is that we not only adding the nodes on the input layer, but also we have added additional nodes on the intermediate level on all these different layers. So that essentially gives us some nice thing that we can maneuver. So the basic idea is as follows. That is, we're going to initialize the value of the larger neural network with the smaller neural network. So here, let's say that I have all these ways that I'm interested. I'm representing them as this bigger matrix. For something that we know already, I use this W1 to represent the block that can be preserved using from the smaller neural network. And then the only thing is that we want to update the weights for the new features, that is the d-dimensional features, and also the intermediate layer features. And the way that we do it is as follows. For the green part, that is the delta WNE, we use the similarity weighted linear combination of the columns in W1. So this is literally examining the feature similarity, and then we want to use the similar weights to combine the weights as before. And then for newer layers, we do not know what will be the similarity, and therefore we're just going to use an empirical distribution actually estimated from the Gaussian distribution. We do not have the slides pictures in here, but in the paper we have it. That is, when we plot the weights of our neural networks, surprisingly, is actually coming from a nicely distributed Gaussian distribution, and that is why we sample from there. Okay. So with that, I just want to say that I think that methodology-wise, that we kind of facing different challenges compared with all the image and natural language processing applications where we have limited number of data. And also the objective is quite different. Instead of trying to look at the prediction accuracy, which we are as well, I'm going to show you the results. A large important part is how do we interpret the results? How do we interpret the features that we learn from the neural network? How do we explain this, or even connecting to causal inference? How we are going to get to there? That is another interest of this particular work. But first, I'm going to show you some classification results. Basically that on ICU data and also on the PhysioNet data set, we compare with some baselines that say that without using the priors, that is incorporating domain knowledge, compared with using the domain knowledge, we can see that using the domain knowledge, we can get a little bit boost in terms of the performance. We also have results compared with other stronger baselines that not based on the neural network. We didn't show it in here, but basically that we can also beat them, but only by a small margin. This similar thing for the PhysioNet, we can beat them, but only by very, very small margin. That kind of motivates us for the second question, right? That in terms of prediction, it is very difficult to say whether we're going to get any meaningful improvement in terms of prediction results, given the limited data, in contrast to the large amount of data we can get access to in the image or the natural language processing applications. And therefore, we want to seek, okay, is there any more interesting insights that we can get from the neural network, that is the latent nodes that we studied? And that is what we did. I didn't put a methodology inside because this is still ongoing work. So what we did is that we want to interpret the features, and also we want to identify what will be the characteristic, or what will be even the causes for the symptoms that we see. In order to do that, what we did is as follows. That is, given this neural network that we defined, and we learned in here, then we're looking at the top nodes, that is the highest level of features that we extracted, okay? And then we want to see, okay, we want to identify these features that are most associated or most probable causes for identifying each type of disease. So in order to do that, we do two types of things. One is that we do a simple linear regression, or doing some looking at the regression coefficients, we can identify some weights. And the other way that we did it is that we actually apply this causal inference algorithm called LINGAM, which is a nonlinear causal inference algorithm to handle the issue of nonlinear causal relationship. And then we also identify a subset of the features that are most relevant or related to the disease that we're interested. After that, we identify the top layer, and then we are going to look at the lower level. That is, we're going to identify the patients that is most associated with the particular higher level feature that we learned. So this is done by actually looking at the ways. We're also doing a shallow learning, because recently there's this technique from Rich Corona that is shallow learning can actually get similar performance as the deep learning. So therefore, what we can do is that we can just train a very shallow one by getting the weights, by training them on the features I learned using the deep neural network. And then so that we can identify on the bottom level, that is on the examples on each patient, we identify a subset of the patients that associate with it, with the features that we identified. And after that, we plot the results, which is showing here. So here you're going to see that we plot the time series observations for different time series variables that we're interested, and then you see this blue one that will essentially be the mean of those most representative patients. Okay, and then you also see these shades. This will represent essentially the variances. The smaller the value, this means that there's not much variances. This will be more characterization. And then we also plot the red dotted line. This is essentially the mean value for all the patients, so that you can see whether there will be an offset or distinguishing from the regular patients or from all the patients. So these are the selected features, of causal inference, that is the Lincoln algorithm for the circulatory disease category. And then we can see that there's this elevated blood pressure, and now I can't even see which one of them is, I think it's probably these ones. And also the heart rate and the depression pH level, they are all good evidences of this particular disease. And there's also some other features that we identify, that is the elevated urine output. This may be also related to the urine disorders, which kind of related to the circular disease. So I'm just using this example to show that how we can visualize the results, or how we can interpret the features that we learn from the neural network. That just seems that this representation can give us some insights to explain what is going on. Another example is this septic shock and related conditions. And this feature is selected by Lasso. It's just representing different examples. And we can see that is we have very irregular physiology, let's say in this part, or the lower pH level. These are all indicative of the septic shock symptoms. I mean, the doctors can do a much better job. I'm just explaining to you what I learned from the doctors. But hopefully, using these two examples, I can show you that is, in terms of interpretation of the high-level feature that we learned, there's still a lot of ongoing work, and we have just gave a first trial in terms of how to do it. And hopefully next time when I talk to you guys, that I can show you more results of how to interpret the features we learned, and also how we can associate them with the possible causes for the disease. Okay. So I just want to summarize. I know that I lose people's attention after an hour. Basically, that there are a lot of interesting research work that we can do for mining and learning time series data. This talk, I only show examples. There are more of them that we publish. If you're interested in a specific question, I'll be happy to talk offline. And finally, just thank everyone, and also thank you guys for staying with me, and thanks, Shuji, for inviting me, and thank you. Yes, go ahead. Oh, okay, go ahead.
I was wondering what the doctors thought about doctors think about just like validate your stuff.
Oh.
I mean, it seems plausible suspicious, but I'm not an expert.
Yeah, so I think that the doctors find it's a cool algorithm, but we just explain to them because it has very nice asymmetric information in there, how they capture it with the nonlinear relationship. They like the idea, and when they see the results, as I mentioned, these are kind of more like these hand-picked results, and some of them are quite impressive, so they're happy with that. But obviously, there are a lot of garbages, and there are a lot of, I guess, mixing noises in there. So,
What do you call it, right? So ultimately, either you run a trial to find out if it's right, or you ask the doctor. So the algorithm may be very nice. And, I mean, you expected it wouldn't get it all.
yes.
What do you actually, how can you validate what it does?
Yeah, I mean, in this particular application, healthcare is hard. But as I mentioned to you, that we do have, we also apply this to climate application. In there, the data is very different. They have large amount of data. We can learn more meaningful things, and also they have the simulation model, which is mostly physical based. And in there, that we can vary the values that we learned in here in the simulation model to see the impact. Then you can essentially do some interventions to validate the results. But in this one, it's a little bit hard. We haven't moved too far by just talking to the doctor and they say, oh, that's nice. We haven't moved far beyond that. I don't know if Sushi have any good ways to validate a lot of the hypotheses that we have in medicine, or the I guess the discovery that we get from the machine learning algorithm. How do we validate them? Yes, go ahead.
So back on that slide,
Uh-huh.
we were sort of initializing the weights that you learned from a simpler structure, and then you're going to add on another feature.
Yes.
So how did you decide, for example, what was the process for deciding which node to add next? For example, is there going to be another hidden node on this layer?
Oh, that is the architecture, right? I mean, we kind of just adding the nodes on each layer proportionally. So,
Okay, so you added one, you sort of went up like in a particular.
yeah, we just add them proportionally. I mean, obviously that there is another problem, that is learning the neural network architectures. That's another real problem. I think that right now we are facing so many problems and challenges when we apply the algorithm to healthcare application, to another application with sufficient number of examples, because there are so many things that can prevent the algorithm work, and we never know that. It's hard to validate what is the reason why we got the improvement and why we're not seeing the improvement. Yeah. Okay. More questions? All right. Thank you so much, and we will have lunch.